I wanted to go ahead and get started pretty quickly because this is another one of those lectures that probably has too many things in it, but we'll get through hopefully all the important things and make sure that everybody understands them as well along the way. But remember that last time we started doing junk to our processor because we realized there was all kinds of stuff we couldn't do with it. Like we couldn't loop, which was a drag. So we said, let's make it so we can loop. Let's make it so we can have a much larger memory without having our instructions blow up to 150 bits or whatever. Okay? And we talked about how we might add various different operand types as well. So we talked about all of these interesting ways that we could enhance our processor. And you'll see processors in the real world that are enhanced in all kinds of different ways, which is pretty cool. It's pretty exciting. What we're going to do today, though, like I say here, we can implement more interesting programs. We talked about doing multiplication. Now, here's the thing about multiplication. Seems like the kind of thing we might want to use a lot, right? So we have a couple of choices. We could either plop down this sequence of instructions every time we want to multiply two numbers, or we could figure out a way of making this callable or accessible from various parts of our program so that we can have this building block that we reuse over and over again. So these are kind of the things that we might want to do with our programs. Here is an example. We want to compute the discriminant. I have no idea why. It's just a nice simple example. B squared minus 4ac. So we're going to compute the discriminant of a quadratic function that evidently uses ints only. Okay, so, but anyway, we got to compute this, and you can see that we have to multiply a couple of things. We know we can do the 4 times by shifting left 2 bits, right? So while we could use our clever little mole thing, it's probably going to be way slower than just bit shifting left, and that's a common choice that compilers will make. Oh, you're multiplying by 4, let's just shift you over 2 bits. So that's fine, but we still have to do b times b and a times c, and we have to subtract. We can do all these things. We're happy, right? We know that we can do this in our processor, but we would like somehow to reuse our multiply function. Okay, so we're going to turn it into an equivalent program like this. So return mul b comma b minus mul a comma c, and then shift that left 2 bits. Okay, so we'll do something like that. So the question that we have is how to use mul as a subroutine, and it's kind of funny to me because this is one of those kinds of things you always take for granted when you write programs. I never really thought about the vagaries of how you even build machinery to support subroutines until I was faced with this question. What if you lived in a world without them and you had to somehow figure out how to create them? Okay? So we have a couple of things we need to figure out. One is, how does mul take its arguments? Where does mul drop its result so that we can actually pass it stuff and get the answer back? Now remember that I've been saying all along, we have this convention that the arguments will be in the low registers. So like 0 and 1 would be A and B, and 7 would be, the high register would be where the answer comes back. Okay? Just a convention. That's what mul is going to do. Okay? So we'll expect that somehow we can pass mul its inputs and call it somehow, and then we'll get an answer out of the topmost register. Now here's where we start running into difficulty. How do we get to mul and then get mul to come back to us? Getting to mul is easy, right? We all know we could use brz0 mul. That's weird, but we could do it. It's a little gross. The problem is, how do we get back? Everybody see that? That's the issue. Okay. I don't want to go into this too much because we're going to develop it in more detail in a slide or two. But the other issue, notice our little table in the top right of this slide. Do you guys remember what this table is? This is all the registers that mul uses. So whoever uses mul needs to be aware that mul is going to stomp on things or want things to be set up in a specific way. Okay? So we have this issue that mul can't be treated as a black box. We have to know all of its guts and its annoying little details so that we can use it properly. Okay? So the caller is basically left with registers 5 and 6. That's not very helpful, right? This is a little bit of a drag. Okay? So you see that there's problems that we have to solve in order to build this new thing that we're going to call subroutines. That's what we're going to call it. So we basically have to figure out how do we pass arguments and return values. That's one of the things we have to solve. We need a way of transferring control to the subroutine and then have it come back to whoever called it. And that's really the tricky part, is getting it to come back to the appropriate location where it was called from. And then we need a way to isolate the subroutine state from the caller state, because really the caller shouldn't have to care. We'd like it to be a black box. Okay? So the first problem, a way to pass arguments and return values between a caller and a subroutine. Well, this is where this magic word convention comes into the picture, and I've already been using it a number of times this term, but it is absolutely the right way of thinking about it. We just need to come up with a set of rules that everybody agrees to follow, and if everybody follows them, we'll all get along. Okay? That's really all it is. Is one set of rules better than another set of rules? Like, if we all decided that we were going to always pass the arguments R7, R6, R5, R4, and then the answer would always come back in R0. Well, we could do that instead, but everybody has to decide to follow the same rules. So that's why it's a convention. It's not like there's some theoretical reason why we do one thing over another. Okay? So that's going to be important because you're going to be following conventions all term. You have to, because the compiler does as well. Okay? The second and third points, those are the ones that we're going to have to put our thinking caps on for and figure out how in the world are we going to implement these different components. So this was our program, and we need to invoke mul twice, and like I was saying, getting to mul is not the hard part. The interesting thing that you'll notice is that I will have discriminant. I'll have the assembly code for discriminant, and I'll call it from one location. And somehow mul has to know, well, it was the first call, so it needs to go back to the first location. And then I'm going to call it a second time, and that time mul somehow has to know it needs to come back to the second location. Okay? So we have to figure out how to get back to wherever it was called from. So here's the question. Are we able to do this with our current architecture? Hey, remember we have we have multiplexers and ALU and registers and junk, and we had wires, and we have this set of opcodes. We only have one branching instruction right now, and it's BRZ. That address is hard-coded into our program. So how do we make mul know where to jump back to? Well, you could come up with some really hideous way of doing it. I just thought of one, and it made me recoil in horror. So you can do it. You can come up with a way of doing this. If you had, for example, a little control flow thing at the end of mul and some little switch you passed in that said, oh, I'm calling it the first time, or I'm calling it the second, so mul would know where to go back to. That's hideous. Okay? You could do that. Okay? But the issue here is the processor only supports constants for branch addresses. We need a way of getting a variable in there somehow. Okay? So we need to upgrade our computer again. You can see that right now, the way that our program counter logic is designed, we have two places that the next program counter value can come from. It can either be the current one plus 1, or it can be a hard-coded value in the branch address part of the instruction. Okay? So we would like to have a way of putting that branch address somewhere else, like, say, in a register. Okay? And that way, if we had something like that, we could just drop the return address into some register, and then mul would always know, well, like, one of the registers is always going to tell me where I need to go back to. Problem solved. Okay? Now I can call a subroutine and get back from it. Okay? And the subroutine is nice and generalized. We don't have to do any crazy hard coding of where I was called from in the subroutine. Okay? So here's what we can do. It's kind of becoming a Franken processor because we're just sort of lumping stuff in there. Real processor designs are much more elegant than this, but bear with us. Okay? So here's our updated logic, and basically we'll have something like this. Okay, notice we had to add a new thing, BRM, to our instruction. It's the last field of the instruction values. BRA is still there. That's the branch address. And then BRM is just, what's the branch mode? Are we jumping to a literal address value, or are we using some register value to do the branch? Okay, and so you can see here in this case, we were using the A register value, or the first source argument, to know whether or not we should jump. There was branch of 0, and A was the thing we were considering. Now you can see that we have a wire coming off B, or a bus coming off B, that says this is possibly the address we want to jump to. So we can now have a variable that holds the address we want to jump to. Everybody good? So as long as we pass correct things, because like obviously now that we have a feature like this, if register B had a bad value in it, we could end up in La La Land. That would be fun, scary, probably not where we want to be, and it probably wouldn't do what we want it to do. Okay, so we have this branch to register thing that we just created, and so again we need to come up with a, oh yes, question?
Isn't it possible that we're using the position that B is in for something else? Like, if we're multiplying two things and then we want to go to something else, the things that we're multiplying are at A and B, right?
Yeah, so here's the thing. That's part of the compiler, basically. Reg B is just going to be whatever is hard-coded into the, remember, the machine code instruction, which will be specified by the assembly code. So that's one of those things that the compiler has to be very careful about. And there's always a big part of compilation that is register assignment. Okay? So, for example, as you'll see on the next slide, we're going to say R6, register 6 is going to be the one that we have the return address in. Well, again, this is a convention, and the caller would have to know, if I want to use this subroutine, I better leave R6, only put return addresses in there. I can't store other things that are important to me because they have to be blown away in the use of this subroutine. Okay? So this is one of the things that compilers have to think about. It's gross. And it turns out that this approach isn't that pretty either, and we'll see a better way to do it very quickly in this lecture. But anyway, yeah, making sure that registers are not misassigned is a very important step in compilation. Okay? I think all of you, once you get through some of these tasks up through assignment 4, you'll start to appreciate how much the compiler takes care of and how effectively it does it too. Okay, so like I say here, you can see the mul subroutine on the right, and we've got this fancy new instruction at the very bottom of the machine code for mul. Branch if 0, 0, so we're just unconditionally branching, to whatever's in R6. We're presuming, and you can see that none of the rest of mul uses R6 so that we don't clobber our return address, but that's basically how we can have the subroutine come back to wherever we are. And so on the left you can see that we have how to call this thing. We need another label. The label points just past where we call the routine from. So move ret into R6. That's going to move the address of the next instruction into R6. And then we jump to mul. Mul does its magic, expecting that the inputs are as specified up there. And as if by magic, we come back and R7 contains the value that we wanted to compute. All right, everybody with me? Cool. No problemo. Now we can actually do stuff. You can see here that I have introduced a move instruction just because it's ridiculous to write add 0 value register. So we're going to go ahead and start using other instructions in this stuff. We should probably just change BRZ to BR, branch, or JMP is very common. Just jump to an address. And so we could do something like that instead of branch of 0. Okay? So please do not be confused by this. It's not rocket science, thankfully. Okay, so our discriminant function. We now have a way of calling mul and returning from mul. Remember, that was one of the things we had to solve. But now we have another problem, which is, one of the other problems that we had in our list. Mul uses a lot of registers to compute its state. Okay, so I have here on the right, you can see that we use just about all the registers now. Register 5 is available. So discriminant, that's all you get, right? if we had a way of encoding constants into our instructions, and obviously we don't have to store 1 and 0 anymore. That sounds like a really great idea. So let's pretend we do that. Now discriminant has 3 registers to use. But this is the real thing we should be thinking. Remember, we love programming in assembly code because it means we don't have to think about machine code. And we love machine code because it means we don't have to think about logic gates or logical components hooked together. And we love logic gates because we don't have to think about physics, right? So why do we have to think about the guts of mul? Let's apply abstraction. Let's turn this thing into a black box somehow so that we only have to think about the arguments. I don't care how mul does its thing. In fact, if somebody came up with a brand new shiny way of multiplying 2 numbers together, I'd love them to be able to drop it right in without having to talk to me about the new registers they use. So that's abstraction again. This is what we'd like to think about. How to pass arguments, how to get the return value back, maybe how to call it and get back to us, but we'll even see if we could simplify that. Okay? We'd like subroutines to use registers however they want. Okay? So we need a way of saving the state of a register, like we were discussing before. Okay, so mul's going to expect its return address in R6, but what if I have something important in there? Well, it'd be great to save it somewhere and then restore it when we're done. And so if you had a particularly nasty subroutine on a processor without a lot of registers, well, that would also be really great because then we could save some registers, reuse them for other things, and then restore the previous values of the registers. Okay? So we implement these things with this amazing data structure called a stack. Now, I know you've probably all seen stacks before, so you can tell I'm being a little bit hyperbolic. But at this level, it kind of is amazing. Okay? This is like one of the few data structures that the processor implements for you in hardware, okay? Which is kind of cool. But a stack actually provides all the facilities we need to implement these capabilities. So we'll start introducing this into our processor design. Okay? So a stack is last in, first out. Whatever the last thing is you put in, that's the first thing that comes out of it. Okay? Easy enough. So we have to have some region of memory that we use for the stack. And you can see, we've got boxes now. I can stuff values into boxes, so this is good. They have addresses and so forth. Okay? I have a stack pointer. Okay? And there is an invariant of the stack. If there is anything in the stack, then the stack pointer points to the last thing pushed onto the stack. It always points to the last thing pushed onto the stack. And the reason I'm making a big deal out of this is that as long as you keep that invariant in mind, understanding push and pop are really easy. Okay? Because you have a couple ways you could do it, but as long as you follow the invariant, then you have one way, and it's always clear. Now, it is a convention on many processors, x86 included, to grow downward. And it is slightly annoying because, a stack, clearly if I have a stack of books on my desk, it doesn't grow downward, right? It grows upward. The top of the stack is the top book on my stack of books. So why in the world would we design it this way? Well, it turns out that we'd like to make sure that we maximally provide resources to programs. And so a lot of times what we'll do is we'll allocate, just dynamic memory allocation grows up from a low address, and the stack is at the top and it grows down from a high address. And so that basically leaves me the maximum amount of time before the two meet and there's an explosion, right? So that's one of the reasons why we grow stacks downward. There are a few processors that can grow them upward, and there's some really clever and maybe overly clever processors where you can control it. You can tell it, I want my stack to grow up, or I want it to go down. Okay? But x86 convention is that the stack grows downward. We have this stack pointer, SP. When we push something onto the stack, SP is decremented, and then we put the new thing there. Okay? When I pop something off, SP is incremented, but first I got to take the thing off the top of the stack. So this is the convention we use everywhere. And there's a lot of programming textbooks that also use this convention because it's a very common convention in computing systems. Okay, so two operations. We have push. We're going to get 2 new instructions. It's really exciting. It's just like Christmas every day in CS24. So push register. So whatever the contents of that register value is, that's pushed onto the stack. So notice the sequence of operations. SP is pointing to the top of the stack. It's the last thing that was pushed on there. So we have to decrement SP, and then we can store the value there. Okay? So decrement and then store. And now SP points at the new top of the stack. Okay? Pop works exactly the opposite. Okay? So we specify a register, and the top of the stack is popped into that register. So whatever SP points to, we'll pull that out of the stack and store it into the register, and then we'll increment the stack pointer because now the top of the stack has gone up. Okay? Now, one slightly interesting thing to notice is, does pop actually clear the contents of the memory that was the top of the stack before? Why would it do that? That would waste time, right? The best work that we have to do, the fastest way to do it is to not do it at all. So in this case, you can see that that memory region is going to end up at some point with old values in it. And so if you've ever wondered why, sometimes you write a program in C or in C++, and you have a local variable in your function, and it's got some value in it. Where did that come from? Well, there was garbage on the stack from a previous invocation. Okay? Not that exciting, but that's why. Okay, so this means that we can simplify our subroutines quite a bit, and we'll see some other things we can do that are even better. So pass arguments and return values in registers. Okay, that seems okay enough. Subroutines will save and restore other registers they use, and the convention is that you leave the stack in the same state as when you got it. Okay, that's the idea here. Okay, so this might be a way of updating mul. Okay, so now we're expecting R0 and R1 to contain the arguments, and we'll drop the result into R7. We still have this crazy return address in R6, but bear with it for a moment. We want to use R2 to compute our temporary value. Remember that we had to look at the low bit of A, so we do a bitwise AND of A with 1. And so we store that into R2, so that's our temporary variable inside of mul. And so we save it at the beginning, and when we're finished doing our computation, we restore it. The caller no longer has to worry about what we do with R2. We just gave the caller another register. How awesome are we? Okay. Any questions? Okay. So here's our discriminant function, and again, we're going to have a convention. So R0 is A, R1 is B, and R2 is C. So we're just using the first registers for the arguments. And the result will go into R7. If somebody were going to use discriminant as a subroutine, we could do something with R6 to go back to wherever it was called from. But here's a way we might do it. Okay. Now remember, mul needs A and B in R0 and R1. So if we're going to multiply B by itself, then we need to save discriminant's value of A so it doesn't get clobbered. So we push R0, move R1 into R0. So now both of those registers are B. We say, I want to come back to ret1. So you store that into R6, and then you call mul. And then magic happens. We don't care what happens, but mul does its thing. We're presuming no bugs, right? And then we come back to whatever is at ret1. Okay? So that's cool. Now remember that the answer is going to be in R7, and we want to call mul again, so we better save our answer. What's b squared? We need to save it so that we don't lose it. So you can see we have a push R7. We restore A back into R0, because we're going to multiply A and C this time, so we move R2, which is where C's stored currently, and we move that into R1. So now R0 and R1 are set up with A and C, and we say, hey, mul, now we want to come back to ret2, and we invoke it. Okay, everybody with it? Cool. So we did all of our multiplying work, and now it's just assembling the answer, right? So we restore b squared. Notice that pop lines up with that push R7. That's the corresponding pop in this case. So now we have b times b in R1. We take R7, which was a times c. We shift it left twice so that now we have it multiplied by 4, and then we just compute our answer into R7. Okay? So this does, somebody asked like several lectures ago, could you have a register appear in both the source and a target of an operation? And it's like, why not? It's freaking slideware, right? We can do whatever we want, you know. We have the launch spaceship opcode or something. So anyway, we just subtract R7 from R1 and we store the answer in R7 and we're finished. How cool are we? Okay, any questions? But you can see now that we have this facility of subroutines, and not only that, but it's not half bad to use because we have a stack to save and restore values onto. Okay? So that was nice. Oh yeah, so you're just spelling it all out, even though we kind of already went through it. We computed b squared. We needed to save a before calling mul, because that wasn't going to factor into that computation. And then we had to save the result of our multiplication as well. And the one thing I do want to point out here is that you are not required to pop things back into the same register that you pushed it from if your program doesn't need it. Okay? Obviously, you do that when you have to. But the stack is a nice general facility. Store something from one register on there, and then later on you're like, you know, it'd be cool to put this in another register. Well, pop it into another register. No biggie. Okay? So, really nice. Now, the stack is so awesome. Let's see if we can add even more things to use the stack. And it turns out that passing return addresses on the stack is a really nice simplification and improvement over our current thing. Because you notice that we always have that little fix-up or weird preamble that we have to do. We have like move whatever the return address is into R6, so that ties up R6. And then we jump to the subroutine, and then we have to have a label saying where to come back to. What if, I'm sure none of you have ever had a copy-paste bug. I had one like a week ago. But, you know, you say move ret1, R6, blah, blah, blah. And then later on when you're doing the last part of mul, or the last part of discriminant, you copy-paste and you forget and leave the move ret1. You forget to change it to move ret2 instead. And now you have an exciting infinite loop in your program. Everybody loves those. Okay? So this is too complicated. And anything that's complicated is going to be a little bit error prone. So we're going to introduce some new instructions that make life even easier. Okay? One is called call. And this is specifically for invoking subroutines. Okay? That's the whole purpose for call existing. I mean, there's other things you can do with it as well, but it's just, this is a really neat thing you can do. Okay? Notice call and then address. This says, I want to invoke the subroutine at address. So we might say something like call mul, so that we can invoke the multiply subroutine. But notice what it does. It basically does that whole move ret1 into R6 thing. It takes care of that for you automatically, but it uses the stack instead of a register to save the return address. Okay, so it pushes the program counter of the instruction following call onto the stack, and then it sets the program counter to be the address you specify. Okay? Everybody understand why we want the program counter of the next instruction? Like when we come back, we don't want to call again, so you get another fun, exciting infinite loop. So we want the program counter for the next instruction so that when we return, we go back to that instruction, the very next instruction. Okay? Then we have another instruction called ret. Ret is very simple. It takes whatever is the current top of the stack and assumes that it's a return address. So it pops that off the stack and stores it into the program counter. That transfers control of the program to wherever the top of the stack said. Okay? What if you don't manage your stack properly and when you ret, it's not a proper address? Probably have experienced this at some point, or you will in this class, almost certainly. You end up in La La Land again. You know, a place that's not even fun to visit. Okay? Any questions about these two new instructions? All right. These are important. These are going to be your bread and butter for like the rest of the freaking term. Okay, so now we don't need our stupid ret1, ret2 labels. In fact, we don't need those move ret1, R6 things either. And guess what? We freed up another register for people to use. Okay? So this is really nice. And it actually starts being kind of intuitive looking assembly code because you set up A, set up B, call mul. Okay? So how easy is that? That's just like really starting to look pretty, if you will. Okay? So caller pushes subroutine arguments onto the stack. Oh yeah, so this is an interesting one. We are actually changing this even more. Okay? Because remember, we were previously passing arguments in registers. Why not see about passing them on the stack? So we'll try this now. Caller pushes a subroutine argument onto the stack, then they use call to invoke. The subroutine can use the stack for its computations if it needs to save any registers, restore any register values, and so forth. Remember, the whole premise is that the subroutine is going to leave the stack in the state that it found it, okay? And then it'll use ret to return to the caller. Okay? Now this is an idea. And part of the reason why I'm going through this isn't actually precisely what you will be doing starting in the second assignment. But I want you to see how far you can take this idea. It's actually a very powerful idea, and it's used all over the place. And the only reason it's not used on X86-64 is because X86-64 doubled the number of general purpose registers. IA32 used exactly this convention. Okay? But when you have more registers, passing arguments in registers actually isn't a bad idea. Okay? So like I say here, there's several options for passing arguments on our simple processor with 8 registers, which is all we have in our little slideware CPU. Passing arguments on the stack is important. There's not many other nice ways of doing it. Okay? But if we have a lot of registers, we can pass arguments in registers instead of the stack or in addition to passing them on the stack. We actually have quite a bit of flexibility in how we design this mechanism. Okay? So I want to explore this so you can see some of the rationale behind the designs that you will be observing in the next few weeks. So how does the subroutine access its arguments? Okay? Let's say that we are starting to pass arguments on the stack. So I want to do b squared. Remember, discriminant is still, for whatever reason, has R0 is A, R1 is B, R2 is C. So if I want to compute b squared, I just push R1 twice. So now B and B are on the stack, and then I call mul. Inside of mul, the stack will look like what I have on the picture. Okay, you have B, then you have B again, and then you have whoever called mul. Where am I supposed to go back to? Okay? So you can see that if the subroutine is going to access its arguments on the stack, we basically have two choices. We can either pop the return address into some register so that we can get at our arguments. Hopefully many of you are shuddering right now. Or we can just support indirect memory access and say, hey, I'd like to access the values at SP plus offset. That'd be a lot easier, because then I can say like SP plus 1, and that'll be one of the arguments, and SP plus 2 will be the other argument. Okay? Everybody with me? Okay, so you can see how indirect memory access becomes super powerful if we're going to be passing arguments on the stack. Okay? Also, like I say here, our stack grows downward, and so you could ask the question, do you want to put, again, convention. I just want you to understand that there's many ways to design this, and there's not one right way. Different ways will have different strengths and weaknesses, but there's not a right way of doing this. Right here, I'm asserting that the first argument is pushed first, and the second argument is pushed second. There's nothing preventing you from pushing the last argument first, and then pushing them in reverse order. Again, that's been done historically for a long time, that we push arguments in reverse order of their specification in C. Okay? Don't have to think about that right now. Thankfully, you probably won't have to think about that very much throughout the term, because we just have so many registers. Okay, so mul modifies registers. If we continue using R2 for computing our bitwise AND, then we need to make sure we save those. So we could go ahead and push those things onto the stack so that we can leave the register state the same as we found it. Okay? Now we have an interesting challenge. where are our arguments? SP plus 0 is our R2 that we saved. SP plus 3 is the return address all of a sudden. SP plus 4 is one of our arguments, and SP plus 5 is the other argument. Okay? So now we're annoyed. Now life just got a little bit more complicated and a little less enjoyable. We're going to spend a little bit more time at work. Because as we push things onto the stack, our offset to where we have things that we want to access changes. And so you can imagine if you had this mechanism as your subroutine executed and pushed things onto the stack and then popped things off the stack, if it's referring to the arguments, the offsets would be changing all the way through the subroutine. What a drag that would be. Okay? Who wants that? So what we do to simplify the interaction with the stack is we save a frame of reference. We save a special location in the stack where we know we can always access the arguments with specific offsets. And so many processors include this thing called a base pointer, aka a frame pointer. Okay? And so the base pointer is the first thing that we set up when we enter into the subroutine. We say, you know what? Somebody may have been using the base pointer. If you have a subroutine calling a subroutine calling a subroutine, you can't assume that you're the first one to be using that base pointer. So the first thing you do is you save the old value of the base pointer, and then you set the base pointer to be the stack pointer. Okay, so you end up with something like this. Okay. The whole rationale for this is instead of accessing arguments using the stack pointer, which may move quite extensively as the function executes, well, I can just access them through the base pointer instead now. And it's great because the pattern is ubiquitous in your generated assembly code. You know, like I have here. Whatever this thing is, return address is at BP plus 1. The old value of BP is at BP plus 0. Okay, it's just memory, so we just have addresses and we just have values. Argument 1 is always at BP plus 3. Argument 2 is at BP plus 2. Okay, so we could do something like this. Any questions? So the whole idea here is that since the stack pointer moves through the execution of the function, why not set up a fixed frame of reference and use that instead to keep life simpler? Okay, so this is our discriminant function. Push R1, call mul. And this is how mul might work inside. So notice the very first thing we do, we save the base pointer because we want to set it up for ourselves. And then we move the current stack pointer into the base pointer. This is also known as setting up our stack frame. You may have heard the term stack frame before. Okay? And then we go on and do our magic. Push R0, R1, and R2 because we use them. And then we can go ahead and start pulling arguments off the stack to utilize for our multiplication. How cool is that? We're getting to the point where all of the communication is going through the stack. So callers of mul don't have to think at all about how mul does its computation. What registers does it trample on or anything like that. Okay? So this, like I was saying, is called the stack frame. This is the part of the stack that's being utilized by one specific function invocation. Okay? And you can imagine that different functions would have different size stack frames. You have one function that maybe just squares a number. And so it doesn't actually need a lot of space to square that number. But then you have another one that maybe it computes a hash code for a string, and maybe it does some other things. You know, you can imagine a complicated function, and that might need a lot more space for its frame. Okay? But this notion of a stack frame is really useful because each function invocation gets its own little bit of the stack, and that allows you to support recursion because you just have the function is using the stack, and then it recursively calls itself, and you get a new stack frame below the old stack frame, and so forth. And since we always leave the stack in the state that it was in when we got called, we pop all of our junk off of the stack, and we basically clean up our frame before we go back to the caller. So it's a very powerful mechanism for supporting subroutines. The kind of programming that I think we're all really used to doing. Okay? So BP is the frame pointer. That's basically the anchor for the frame. And since we have programming languages where usually we always have a fixed number of arguments, don't talk about variadic functions, we aren't going there today or ever in CS24. We can expect that we always know how many arguments there will be. So we can generate the assembly code knowing the offsets. We're done, right? It's like mic drop. We're finished. Okay. And x86, in fact, has a base pointer register specifically for this. Quite a few processors do. Okay, any questions? Okay. What we're going to do now is start talking about real processors, because why keep generating a slideware processor that has all the things that x86 can do? Why not just talk about x86? Okay? So we have all these neat features now that we've talked about in the last handful of lectures. So we're going to start talking about x86. And this is kind of a family of instruction set architectures that are all backwards compatible to the original 8086 processor, which is actually not the first processor that I programmed. I programmed an 8088 as my first processor, which was the 8-bit data bus version of the 8086. Okay? Same instruction set, though. Okay, so x86-64, it has 16 general purpose registers, and it has all of these abstractions and even more. Like, it's crazy. It really can take your dog for a walk and make you breakfast. I mean, it's a pretty fancy processor as far as capabilities are concerned. Okay, so like I was saying, this is a family of instruction set architectures. x86-64 happens to be the latest iteration of this ISA, and it's for 64-bit data buses. Okay, and so the first processor, like I said, was 8086. That was 1978. Probably a bit before you were born. It's a bit after I was born. And you can see that it only had 29,000 transistors, which I find mind-boggling. Does anybody know how many transistors are on current x86-64 processors? We're talking 2 to 3 billion. Okay? A few more. Okay? So this line of processors continued to be developed. I don't know if, does Glenn still use 186s? I got to program one of those in 5X when I was there. So anyway, you have all these various processors that came along. I've had many of these as personal computers, and you definitely noticed advances in sophistication and capability. Okay, so Pentium-4 was where we finally got 64-bit support, and we also have this magical thing called hyperthreading, which just leverages the superscalar architecture of the processor to run multiple threads of execution at once on a single CPU. Okay? And so then many people now are using Core I-series processors, which are really clever, and I'm not even going to talk about all the clever stuff because I don't want to get ahead of myself, but they're really powerful and definitely worth taking advantage of for computation. Now here's the madness. This whole processor line maintains backward compatibility. So if you happen to have a computer that you just got in like the last 6 months, and it's like the most badass computer that any of your friends have, well, guess what? When it boots up, it acts exactly like an 8086. So then the bootstrap has to like turn on all the other features because they wanted to maintain backward compatibility, and that, backward compatibility actually is a source of much insanity in many circumstances. Okay, for example, word size. Words normally are the size of your data bus. You say, this is one word, and if your data bus is 8 bits, a word is 8 bits. If your data bus happens to be 18 bits for some reason, your word size is 18 bits. Well, not on x86. On x86, word size is 2 bytes, because that was the original word size of the 8086. Okay? So even on our fancy 64-bit processors, the word size is still 2 bytes, which is really bewildering. Okay? So basically what we have to do is figure out how many words fit together into the size of the value that we're talking about. And then you put on the stupid English prefix for it. So quad words or Q words, 4 words, so you've got 8 bytes. Okay, so that's going to be 64 bits, and that's what you generally work with. Okay, a pointer will be a quad word because we need 64 bits for the data bus. Okay, double words, a D word is going to be 4 bytes, so that would be IA32. Everything was D words, unless you had a few things that could use quad words. Normally, if you have an int in your program, it's going to be a double word. Okay, a pointer in 64, since we're talking 64-bit x86, it's going to be that a pointer is 8 bytes, an int is 4 bytes. Does anybody remember how big a long is? Because that varies. I believe it varies between 32-bit and 64-bit. Yay. Let me get off this train because it's not going where I want it to. Okay, so registers. We have a whole bunch of registers that we can use, and they're all quad words. So we have RAX through RDX. Again, why do we have these named RAX through RDX rather than R0, R1, R2, and R3? Well, because whoever designed it thought it was a good idea. RSP is the stack pointer, so this is what stack operations leverage. You have RBP for the frame pointer, aka the base pointer. Okay. RSI and RDI, so these are for string operations, which are, again, this is a CISC processor, so if you want to do a string comparison, processor has support for that built in, which is crazy. Okay, and it doesn't support Unicode, so don't use it. Okay, let's see. So RSI, RDI for string load, move, and store operations, and then you have the other 8 registers that showed up in this ISA. So R8 through R15. Okay, why not? I guess it's good that they didn't do like RM, RN, RO, RP. That would make me sad. Okay. Now these are all quad words, 64 bits. All right. We can access components of them, which is weird, but it totally works. So let's say we have RAX, just as an example. The low half of RAX can be accessed through EAX. It's just a nickname for the low half of RAX. AX is the low word of RAX. So you could write to AX and then read RAX, and you'd see the low 2 bytes were what you just said. Okay? And then you can even further refer to AH and AL as the low byte or the second byte. Now, AL is the low byte and AH is the high byte. The high byte of the low word. Okay? Everybody with me? Okay. Anyway, RSI, RDI, and what was the other one? SP and BP. You can see that we have these. Notice they're not quite as fancy as AX, BX, CX, and DX, but they're still kind of like the difference between these registers and the previous registers is we don't have the notion of like AH, accessing the second from the bottom byte. Okay, because these are all pointers. These registers are used for pointers most of the time, or at least that was their original design. You can use them for whatever you want. But since they are designed to be pointers, that's why you have RSI, then ESI, then SI, and SIL. Okay? But there's no such thing as SIH. Okay, R8 through R15 follow the same pattern as the other registers that we just talked about, RSI, RDI, and SP and BP. Okay, R8, R8D is the low half of that, R8W is the low quarter of R8, and then R8B is the low byte. Okay, and there's no like R8 low byte, R8 high byte. Okay, everybody got it? Okay. Let's see. These registers are broken down this way for a lot of reasons. And one of the reasons is that sometimes we only need a 32-bit value. Remember, ints are 4 bytes. So my assembly code should just use ESI, or it should use EBX. It shouldn't actually use RBX because it's only a 32-bit value in my C program. Okay, so we have situations where the assembly code refers to those. Also, we have the grim specter of backward compatibility. So you should still be able to execute 8086 code on this fancy pants Core i7 hex core with hyper-threading and all that malarkey. Okay, so it refers to these registers and the processor needs to support accessing just the small little chunks of them. Okay, so that's part of the reason why. All right, yeah, so IA32 can access 32-bit registers, but not the R8 through R15. IA32 can actually refer to 64-bit registers, I believe. There's all these weird things you can do. X86-64 can access everything. Okay. All right, so two other registers. You have RIP, which may be what your program does sometimes. This is the instruction pointer. So again, X86 calls the program counter something slightly different. It calls it an instruction pointer. You cannot access it directly. You set it by jumping. That's how you load a new value into the instruction pointer. Okay? Or calling. R flags is the flags register. This is where you have your state from computations. So add overflows, well, that shows up in R flags. Okay, let's see what else we have. Yeah, so since we're almost out of time, I want to make sure that we talk about things that are actually important. Oh yeah, so you all know what a pointer is, I hope. You're probably seeing this in all kinds of gory detail now in this class. Pointers do have a couple things. A pointer is an address where a value lives, but a pointer also has associated with it, at least in the higher level program, it has information about what type is pointed to, so that we know how large the thing is. Okay? And so that's kind of important. X86-64, I already talked about this. You know what, I'm going to go ahead and skip this. You can read about that. That's not very exciting. This is also not very exciting. One thing to know is that, yes, there are a bunch of other fancy registers, like for doing floating point. What you'll notice is that assignment 1 is like the only place we do floating point, because we're going to start doing assembly programming, and I don't want you to have to think about all these other weird registers. I just want you to stick to the integer registers. It's hard enough. Okay? But you can read about that stuff if you want. Okay? But here's what's important. If you have a pointer to a multi-byte value, you do have to think about what order the bytes actually appear in the memory. Okay? So if we were going to store a 32-bit value, 1, 2, 3, 4, 5, 6, 7, 8. So 78, this is hex, obviously. The value 78 is the least significant byte. 1, 2 is the most significant byte. So we could store this in two different orders. We could either store big endian, where the most significant byte is at the lowest address, or we could store little endian, where the least significant byte is at the lowest address. Do people know where these terms big endian and little endian came from? Gulliver's Travels. Evidently there was a war between two peoples who disagreed about which side of a hard-boiled egg you should start at. Seriously. So, illustrating the relevance of this decision, I mean, again, it's a convention. People name them big endian and little endian. It's important to understand that X86 is little endian, which means the least significant byte is going to be at the lowest address. So you have a multi-byte value. The pointer to it is going to be at the low byte of it, and that's also going to be the least significant byte, and then you consume n bytes. Okay, any questions? That's all we need to talk about today, so we'll wrap up, and I'll see you next time.